Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 3. Iterative Methods, Gauss-Seidel and SOR Methods. In Video 2 of Chapter 3, we stated that any system of linear equations might be expressed fixed-point iteration form. However, how the current or prior estimates are incorporated in the subsequent iteration equations depends on the method. The Gauss-Seidel iteration equations are set up as follows. Here, we introduce the superscript notation to indicate the iteration steps. The Gauss-Seidel method, on the contrary to the Jacobi method, uses the current estimates immediately in the subsequent iteration equations. For example, the current value of x1 is available when moving on to the second equation, so it is used in the computation of the current estimate of x2. Similarly, as we move on to the third equation, the current values of x1 and x2 are available. Hence, they can be used in the third iteration equation. This procedure is applied for all equations from I equals 1 to n. The generalized and most suitable form of the Gauss-Seidel iteration equations can be expressed as follows. Here, x superscript p and x superscript p plus 1 notations denote the estimates at the prior and current iteration steps, respectively. The mandatory requirement is that the diagonal elements of the coefficient matrix be non-zero. The benefits of the Gauss-Seidel method are: the method is easy to understand and program. It is a special case of the SOR method with omega equals 1. The method is neither computationally complicated nor involved. It generally converges twice as fast as the Jacobi method. It converges to the correct solution regardless of the initial guess. It requires less memory compared to faster iterative methods. The drawbacks of the method are: the method does not converge for every system of linear equations. It is applicable to strictly diagonally dominant or symmetric positive definite matrices. It is, in general, not competitive with the non-stationary methods. Unlike the Jacobi method, computations generally cannot be carried out in parallel. Parallelization depends on the properties of the coefficient matrix. Now let us consider solving the following 3x3 system of linear equations using the Gauss-Seidel method. The initial guess vector is going to be taken as the 0 vector. The Gauss-Seidel iteration equations can be explicitly written as follows. Note that in the second equation, the current estimate of x1, which is available, is immediately used. In the third equation, since the current estimates of x1 and x2 are available, they are used. We define the displacement as the difference between the current and prior estimates. Of course, we would like to have the displacements go to 0 as quickly as possible as the number of iterations is increased. Here we will be tabulating the computed estimates and the absolute value of the displacements as they are calculated. The first row estimates are the initial values, which are set to 0. Since there are no prior estimates, locations reserved for printing the displacements are left blank. For p equals 0, the iteration equations are as follows. Using the first equation for x1, which uses prior estimates of x2 and x3, yields 1.25. The second iteration equation for x2, using the current estimate of x1 and prior estimate of x3, gives minus 0.125. And the third equation, using the current estimate of x1 and x2, yields 1.28125 for x3, which is also the displacement. Now that we have the first step estimates, we can determine the infinity norm of the displacement vector, which we will use to monitor the convergence of this iteration process. We observe that the largest displacement, 1.2813, is observed for x3. For p equals 1, the Gauss-Seidel iteration equations are written as follows. The first equation for x1 requires the prior estimates of x2 and x3, which gives 0.96938, and the absolute displacement, 1.25 minus 0.96938, yields 0.2891. The second equation requires the current estimate of x1 and prior estimate of x3. Upon substitution of these values, the current estimate for x2 is found as minus 0.621094, and the absolute displacement is obtained as 0.4961. The third equation for x3 requires the current estimates of x1 and x2, which yields 1.725,586, and the absolute displacement yields 0.4443. At the end of second iteration step, the maximum displacement is observed to be 0.4961. Continuing the Gauss-Seidel iterations in this manner yields the following table. Note that the unknowns converge 4 decimal place accurate estimates after 13 iterations. Recall that the same system was solved by the Jacobi method in 57 iterations with the same level of accuracy. The SOR method, successive over relaxation, is another iterative numerical method for solving systems of linear equations, particularly for large sparse systems that arise in many scientific fields. It is an enhancement of the Gauss-Seidel method. The over-relaxation part refers to the process of using a weighted average of the current and prior SOR estimates during each iteration, which can help accelerate convergence. Where omega is so-called the relaxation, or acceleration, parameter. Here, XGS refers to the Gauss-Seidel estimates. The SOR iteration equations can be explicitly written as follows. Note that the iteration equations are the weighted average of the prior SOR estimates, i.e., the first term, and the estimates due to the Gauss-Seidel iteration equations, i.e., the second term. Here, omega is a weight factor, and the choice of omega significantly impacts the convergence rate of the method. Generally, there is an optimum value of the acceleration parameter for which the number of iterations is minimum. This topic is covered in the next video. Also notice that the iteration equations immediately use the current estimates as soon as that become available. The generalized form of the SOR iteration equations is expressed as follows. Here, x superscript p and x superscript p plus 1 notations denote the estimates at the prior and current iteration steps, respectively. The mandatory requirement is that the diagonal elements of the coefficient matrix be non-zero. The benefits of the SOR method are: the basic SOR algorithm is easy to understand and implement. It converges faster than the Jacobi or Gauss-Seidel methods. The iteration process is accelerated for omega values between 1 and 2. However, the linear systems that diverge with SOR may converge for omega values between 0 and 1. There is an optimum value that results in the fewest iterations, or least CPU time, and the highest convergence rate. Adaptive SOR algorithms that estimate omega optimum are available. Parallelization depends on the structure of the coefficient matrix. The drawbacks of the method are: the method, like Gauss-Seidel, may not converge for every linear system. The coefficient matrix must satisfy certain properties, as covered in Section 3.3. Its performance can be sensitive to the choice of omega optimum, which is difficult and costly to estimate beforehand. Solving a linear system without a smart estimate for omega optimum can lead to a large number of iterations, which may be worse than that of the Gauss-Seidel method. Consider solving the same 3x3 system of equations with the SOR method. The SOR iteration equations can be written as follows. The second equation immediately makes use of the current estimate of x1 as it becomes available. The third equation also makes use of the current estimates of x1 and x2, which helps speed up the convergence of the system. The displacement is defined as usual. We will tabulate the estimates and the displacements as they are calculated. The first row estimates are initial values, which are set to 0. For p equals 0, the SOR iteration equations are written as follows. Using the first equation for x1 yields 1.625. The displacement at this step is also 1.625. The second iteration equation with the current estimate of x1 and prior estimate of x3 gives 0.40625. The displacement for the second step is also 0.40625. The third iteration equation for x3 using the current estimates of x1 and x2 yields 1.817968. At the end of the first step, the infinity norm of the displacement vector, that is, the largest magnitude displacement, is 1.8180. For converging systems, the displacements should approach 0, hopefully as quickly as possible. As we continue the SOR iterations in the same manner, we obtain the following table. Note that the unknowns converge to 4 decimal place accurate estimates after 8 iterations. The approximate solution was obtained faster than the Gauss-Seidel method, which converged in 13 iterations, and the Jacobi method, which converged in 57 iterations as illustrated in video 2 of this chapter. That is all for now. See you next time with another topic. Bye.